This section is entitled Piecewise Defined Functions and Power Functions. We're going to talk about the power functions first. Let's look at power functions. The form that a power function appears in is in the first box on the left. We have a number that's a real number as a coefficient a times a variable, usually x, raised to an exponent. And again, a and b represent real numbers. Notice, however, there's only one term in a power function, so power functions contain only one term. Well, let's look at some examples of some power functions. Let's look at one that you're familiar with from a previous section. A quadratic equation that only has one term is a power function. So we have a being 3 here and b being 2 there. Let's look at some other ones. There are many types of power functions. Another type, negative x to the 5th. Here the a is, of course, negative 1 because when you don't have a coefficient, the coefficient is actually 1. Let's look at another one. Well, I could actually have a variable that had a negative exponent on it, and that's all right too, because negative numbers are real numbers. So here are 3 examples of power functions. Let's look at some special power functions that don't appear in the top table, and they're called root functions. They're special power functions. They're in the same category. Notice that the examples I gave you, the exponents, some of them were positive, some of them were negative, but all of them were numbers that were not fractions. Now let's look at a power function that is actually going to have an exponent that's a fraction. And as you know from reviewing in the homework, that a radical can be expressed as a term without the radical sign if you express it as a fractional exponent, that root functions, or radicals, are actually power functions because these two expressions are equivalent, as you've seen in previous sections. So radicals actually are power functions. So let's go ahead and look at some examples. Again, this is from the review section in your homework. Let's say that I have f of x equal to the square root of x. That's actually a power function because I can write it as x to the 1/2. And I have one term that has a power on it, and those are power functions. Let's look at some more. Let's say that my next one, g of x, was 5 times the cube root of x squared. Well, again, that's actually a power function because we can reformat that and rewrite it as 5 times x to the 2/3. Let's look at another one. H of x. H of x, I'm not going to write as a radical. I'm just going to show you that because decimals are actually fractions in disguise, I could have a power function that has an exponent that's a decimal, 1.45. Or I could have a power function that has a decimal as an exponent that is negative. That's also a power function. Now remember, we assume that you have the skill to rewrite an expression that is in radical form to one that has no radical but has a fractional exponent. This was review homework for this section, or for this course rather. If you do not know how to do this, you need to go to the review section that teaches you how to do this. We will be solving equations that contain power functions graphically, because we do not yet have a technique to solve them algebraically. Example, using a power function in an application problem. Let's look at this application problem. Percent of all Pandoran children that have studied a course in English can be modeled by the function p of x equal to 37x to the 0.39, where x is the number of years since the year 2000. First we want to graph the function for the years from 2000 to 2020. So remember how we usually do that. We're going to have an x max that's going to be equal to 0 because that represents the year 2000. And then we're going to have an x min set up at 20 because that x equals the year 2020. And then we're going to use a zoom fit on it. So let's go ahead and do that. All right, I'm going to go up to y1 and I'm going to type in my function, 37x. Now the way you're going to get that exponent on there is to make sure that you hit the caret key down here. We've talked about that before, but we've never done it for power functions. So you want the caret key down below the clear button. And when you hit the caret key, see what happens? It gives you a little box to put the exponent in when you hit the caret key. So I'm going to put in my exponent, 0.39. I'm going to hit enter. And I'm going to graph that and look at it. Now remember we said we were going to use a window that was 0 to 20. And then we were going to let the calculator do our window for us by doing zoom fit. So let's take a look. All right, let's take a look at that function. So we need to answer some questions about that function. The questions are this. Is the function increasing or decreasing during this period? So we're talking from from 2000 to the year all the way over here of 2020. Well, if you follow the graph is definitely going up as we go through these years. So we know that the graph is increasing. So we'll write that down. Increasing over this period. Now, is the graph of the function concave up or concave down? Well, let's remember something from when we were doing parabolas. Remember when we were doing parabolas and we said the parabola that opens up like that was called concave up? And the parabola that opened down we called concave down. Well, now we're going to expand that idea of concavity to functions that aren't parabolas, because concavity just describes the curvature of your graph. Is it going down like this, or is it going up like that? So let's look at our graph. This is no longer a parabola, but you can see that this graph, if we would extend it, looks more like concave down than it does concave up. So this is going to be called concave down. So let's write that down. So our graph is increasing and it's concave down. Now, the next part of the question that we want to answer is we want to use graphical means to estimate the year when the model predicts that the percent of Pandoran children will be 74. So we want to know when P of x is going to be 74. So we're trying to solve the equation 74 is equal to 37x to 0.39. Well, we've got to do it graphically because we can't do it algebraically. So remember, we're going to have an equation on one side, a number on the other. So we're going to use, again, the intersection method. We've used this several times before. I'm going to go back to my y equals screen. Because I already have this part on y1, I'm going to choose to put the other side on y2. And I'm going to graph them both and see where they intersect, just like I always have. So I'm going to do second calculate, intersect. I'm going to answer the questions as the prompts come up. Yes, that's the first curve, enter. Yes, that's the second curve, hit enter. Go over there to where it intersects, hit enter. And we're going to take that as our number to use for our year. So we're going to go to the nearest whole number, which would be 6. So we're going to have x equal to approximately 6. And that means that our year will be equal to 2000 plus 6, or 2006. In a previous section, we talked about how to take real-world data, make a scatter plot out of it, and then use our calculators to get a regression equation that describes the data. But in the real world, data is messy. And when we want to find an equation that will describe the pattern of the data, we need to have the data stay in the same pattern from beginning to end. But in the real world, as I said, data is messy, and it doesn't really stay in the same pattern from beginning to end very often. And because of that, we need to use something called a piecewise defined function. That's a function where you can have the pattern of your data change from one place on the x-axis to another. But when you use a piecewise defined function, you're going to need to describe the different patterns in the data with different equations. So let's look at what a piecewise defined function is. Let's read about piecewise defined functions. You can read along with me here. In general, rules for most functions can be described by one equation. There are, however, important functions which cannot be described by one equation alone. These are called piecewise functions. They need a set of equations to be completely defined. And as I mentioned earlier, this will be the case a lot for real-world data. This set of equations is comprised of 2 or more equations. Each of the equations in the set describes the function along a particular interval or piece of the x-axis on its graph. Let's look at the example below. Now, I've got 3 separate pieces in this piecewise defined function. Now, in order for us to do this example, I need to give you the values of the equations for each one of these pieces. So what I want you to do is write along with me. So let's put the equation for each piece along the line. So the equation for this piece is y is equal to x plus 1. The equation for the middle piece is y is equal to negative 2x plus 1. The equation for the last piece is y is equal to 2x minus 6. Now, what we're going to do is we're going to take that information and we're going to develop a expression that will describe this piecewise defined function. So let's read again. The above picture is a single function that is composed of the graphs of 3 different lines. The graph of each line comprises a piece of the function. As you can see, the function has 3 pieces. Let's call the function f of x and write its description below. So now we're going to write a description of the function that is pictured in the graph above. Since it has three pieces and we want everybody to know that all three pieces are part of the same function, we're going to start off by doing 1/2 of a brace, or what we call a squiggly bracket. And at the top, I'm going to concentrate on describing this first equation. So I'm going to start with y equals x plus 1. So f of x is equal to x plus 1. So I'm writing the equation first. And now I'm going to write the word if. And I'm going to describe the portion of the x-axis that the equation x plus 1 lives on. So let's go back up and look at the graph. And the portion that I'm going to be looking at right here is all along the x-axis up to here. And the portion of the x-axis that this first line lives on goes up to the point where it stops. And that point right there is -2. So that's -2. So if I was to describe this portion of the x-axis using an inequality, I would say that's a portion of the x-axis where all the x's are less than or equal to -2. That's the portion. The reason I used an equal sign is because I have a closed circle here indicating that I want to include -2. So what I'm going to do now is I'm going to take that info and I'm going to say f of x is equal to x plus 1 if x is less than or equal to -2. So I've done the first piece. Now let's do the next piece. I'm going to write down the equation for the next piece. The equation we decided was -2x plus 1 if, and now we've got to decide the piece on the x-axis where the middle piece is. So it runs from here to there. So I've got all the way from here to there. That's the piece that this line lives on the x-axis. And now I have to describe it with an inequality. So let's describe that with an inequality. Okay, it starts at -2, but it doesn't include -2 because I've got an open circle there. So it starts at -2, and it goes all the way over here to +1. That's x equals 1 right there. But it's got a closed circle there, so it does include 1. So I have the piece that middle part lives on as x is between -2 and 1. Doesn't include -2, but does include 1. So let's write that down as an inequality. Lastly, I'm going to look at the last piece, which is got the equation y equals 2x minus 6. So I put the right-hand side of that equation down, 2x minus 6, if, and then I have to describe that piece that this line lives on the x-axis, and it's right here. And if I look at where it starts at x equals 1, but remember we're looking at this line and it has an open circle, so it doesn't include x equals 1. So it's all the x's that are greater than 1 but not equal to 1. So now we have the equation for that piecewise defined function. And each one of those pieces represents one of those lines that is graphed. But let's remember that when you write a piecewise defined function, the first part is always the equation, and the second part is always the piece of the x-axis that it lives on. All right, let's use that equation to answer these questions. We want to find the value for f of 0, which means the y value when x equals 0. So let's take a look at it. Let's do that one first. Well, I've got 3 different equations to pick from, but I can only use one. I don't use all 3. So I have to find out which one of these equations is good for when x is equal to 0. So I look over at the piece to find out where x equals 0. And x is equal to 0 inside that interval. And so I'm going to use that equation. So I'm going to use the second equation because x equals 0 is in that piece. And so I'm just going to plug x equals 0 into that equation and find out the value. And I find out when x equals 0, f of 0 is 1. Let's do the same thing for the next function value, f of negative 2. Which equation am I going to use for f of negative 2? Well, look in the pieces, find out where negative 2 is. If you'll notice, I have negative 2 here twice. But in this piece, the middle piece, negative 2 is not included because I don't have an equal sign here. So this is the piece that includes x equals negative 2. So I use this as an equation. So I'm going to use the first equation. And then I'm just going to take that first equation and plug in the answer. So I'm going to have negative 2 plus 1 equal to negative 1. Now we're going to look at how to use your calculator to graph a piecewise defined function. There's a special way that you have to key these in, and we're going to do an example and show you the keystrokes that you have to make. And I advise you to write these down so that when you have to do it for yourself, you'll know the technique. Now, let's see the procedure to use in order to graph a piecewise defined function using your calculator. In this course, I'm only going to ask you to graph piecewise defined functions that have 2 pieces. Our last one had 3, but when I'm asking you to graph, I'm only going to ask you to graph 2. So let's look and see how we want to put this on our calculator. Because this represents one function, even though it has 2 equations, I need to just put everything on one y equals line. So I'm going to use y1, and this is how I'm going to key it in. I'm going to take the equation for the first piece, the 2, and I'm going to put it in parentheses. And then I'm going to do another set of parentheses, and I'm going to put the inequality in that parentheses. To get the second piece on, I'm going to do a plus, and I'm going to write the equation for the second piece first inside parentheses. And then on the second set of parentheses, I'm going to put the inequality for that piece. So this was the equation for the first piece. That was the inequality that described where that equation was. This equation that came second. And this is the second piece. All connected with a plus sign. That's very important. Well, let's give it a try. I'm going to have parentheses 2, another set of parentheses. Now don't think this is multiplication because your calculator is programmed to know what you're talking about, that that's not multiplication. Type in x. Now we need to have an inequality sign, and where you find the inequality sign is by doing second math. It's actually under test, second math, and you just choose the one you want. We want greater than, so we're going to choose number 3. Hit enter, and it puts it in there for you. I'm going to type in the 1, end of parentheses, plus. Then I'm going to put the second equation, which this time is a parabola, so I'm going to have x squared minus 4. And then I'm going to put the second parentheses, which is x less than or equal to 1. So I have to go back to second math again. That's going to be number 6 this time. Oops. Let's go back. I went a little bit too far. I need to do number 6. I'm going to have to get rid of that equal. And then I'm going to put in a 1. And then I'm finished. All right, now let's set our window. I'm just going to use the Zoom Standard, see how it works, and hit enter. And you can see the parabola that was in the second line is actually on the left, and it stops right there at 1. And f of x equal 2, which is the equation of a horizontal line, if you remember, is on the first line. So it doesn't always do it from left to right. It doesn't matter as long as the piece is correct. So there you go. Now, let's use our calculators to find the values for f of 1 and f of 5, first graphically, and then we can do it algebraically again. So in order to do that, I'm going to do second calculate. I'm going to use the value, the very first one value, because I want a y value. To find f of 1, I type a 1 in here. I hit enter. And it puts the cursor where my answer is and tells me the answer is -3. So according to the calculator, f of 1 is equal to -3. Now let's do f of 5. I've already got the value menu started, so I could now just type in 5 if I want to. It'll do it for me again. And it takes it over to where that f of 5 is, and f of 5 is 2. If we did it algebraically, if we found f of 1, we would have to look at the original equation and find out where 1 was. 1 is in the second equation. So we'd have 1 squared minus 4, which is 1 minus 4, or -3. f of 5. f of 5 requires us to use the first equation. And remember, when your expression has no value of x, it's always going to be 2 no matter what the value of x. So f of 5 is just 2. f of 6 would also have been 2. Just remember that when you have no x there, the number or answer is always just that number. And so we agree with what the calculator told us. The next function we're going to look at is called the absolute value function. When you first learned about the absolute value function in high school, probably the first definition you were given was that the absolute value of a number is its distance from 0 on the number line. And that's correct, but that's the geometry definition of the absolute value. The algebraic definition of the absolute value function is slightly different. So let's take a look at it. As it turns out, the absolute value function is actually a piecewise defined function. That's the algebraic definition of the absolute value function. Let's look at what it actually is. We're going to call the absolute value of x just plain old x if the value of x is greater than or equal to 0. That means if the number inside of the absolute value bars was a positive number or 0, then when we take the bars off, we leave it alone. But the absolute value of x is going to be negative x if the value of x was less than 0. That means if the value of x was negative. So let's see how that works to give you the same answer you've always been getting when you did this before. This is algebraically how we find the absolute value of a number. Let's look at the first example. Let's say that we wanted to find the absolute value of -3. Well, normally all you do is say, well, when you take off the bars, if what's inside is negative, you turn it positive. But this definition is what is enabling you to do that. Because the value of x here is less than 0, we use the second equation. So here's what we do. We have the absolute value of -3 is equal to minus whatever was in there. And when we do minus a negative number, it turns it positive, and that's how we actually get the negative off of the absolute value number. Through this definition, that's actually what's happening. But all our lives, we've just known that when we take the bars off, the absolute value of a negative number is its positive number. Positive version of that number, rather. Let's look at the second example. Let's say we had a +3. Because this value of x here is x equals 3, it's in that piece of the piecewise defined function. And so we use that part of the definition for our value. And so when we have the absolute value of 3, we're going to have that equal to just 3, because that's what the definition said. If the number inside is positive, the answer when you take off the bars is just the number itself. So even though we've been doing that all our life, this is the reason you're able to, when you take the absolute value of a negative number, write it as a positive number. And when you're taking the absolute value of a positive number, you just let it be exactly what it was to begin with. The final thing we're going to do in this section is we're going to solve absolute value equations algebraically. Now, an absolute value equation is simply an equation that contains absolute value bars. But these equations are different from any equation we've done so far. When you solve an absolute value equation, it is possible to get an erroneous or false answer even if you've done everything correctly. So this is one type of equation that you must check your answers on. Let's look at some absolute value equations. Solving absolute value equations. The big thing that we want to remember, as I stated earlier, is that you have to check your solutions, because you can do everything right algebraically and still have a solution that is false. So let's take a look at the first example. The first step, or the major step, is when you're solving an absolute value equation, is you want to rewrite this absolute value equation as two equations without absolute value bars. You can't solve an absolute value equation with the bars on it. So what we're going to do is we're going to rewrite this as two separate equations. Now, because the expression inside the absolute value bar can either be 6 or -6 and still make the equation true, because remember, the absolute value of -6 is also 6, then we have to make sure that we write the two different versions of this, the two different things that can happen. So the first time we write it, we take off the bars and we write it exactly the way it is with no changes. The second time we write it, we still write what's inside the bars exactly the same without a change, but we put a negative in front of the right-hand side. So the technique is to put a negative in front of the side without the absolute value bars. That's going to be our technique when we do all the problems. So the first time we write it just as is with no changes. The second time we write it, we don't change what's inside the bars, but we do put a negative in front of the side that's not inside the bars. So we have our two equations now that we want to solve. And so what we do is we just look at each equation individually and we solve it using a technique that will work for that particular type of equation. Well, let's look at the first one. X squared minus 5x equals 6. Well, obviously that's a quadratic equation. We're going to solve it algebraically, which means we've got to get 0 on one side and everything else on the other. Now, at this point, I don't care if you use the quadratic formula to solve this for x, or if you factor it. But you will find that most of these quadratic equations that you're going to have to solve when you do the absolute value function are going to be very simple. So it's actually easier to factor these. This factors x minus 6 times x plus 1. That gives me values of x equals positive 6 and negative 1. So I got two values from the first one. Now let's look at the second one. Again, I'm going to get x squared minus 5x. I'm going to get 0 on the other side, so I'm going to add 6 to both sides. And then I'm going to factor that again. That's going to give me x minus 2 times x minus 3 equal to 0. And again, that's going to give me values of positive 2 and positive 3. So I have actually 4 values of x that will make the original equation true. But what you have to make sure to do is to check each answer in the original equation to find any false solutions. All right, so what I have done is I have already done that check, and I'm going to show you how I plugged in each one of these values, 6, negative 1, 2, and 3, into the original equation. Let's see what it looks like. All right, I'm checking x equals 6. I plugged x equals 6 into the original equation, this one right here. And I wanted to see if the left-hand side turned out to be the same as the right-hand side. And as I did each one of these, I turned out to get 6 equal to 6, so that checked. That was a good answer. X equals 6 was a good answer. And I'm going to check x equals negative 1. When I plug negative 1 into the original equation, I get absolute value of 1 plus 6, which is the absolute value of 6, equal to 6. And of course, that checks. So that solution is good. So both of the first two solutions were good. Next one, x equals 2. Plugged it into the original equation. I ultimately got the absolute value of negative 6 was equal to 6. Well, that means 6 is equal to 6, so that's also correct. Lastly, I got x equals 3. I'm going to check it. I plugged 3 into the original equation. Eventually got the absolute value of negative 6 is equal to 6. And that one checked. So I did a lot of work, but I found out that in this particular case, all my solutions were correct. So when I go back to my original problem, I know that I don't have to eliminate any of these solutions, that they are all correct. Now, let's look at another one. we're going to use the same technique we used before. We're going to solve this equation, and we're going to set it up exactly like we did before. We're going to have two equations. The first one is going to be the original equation without the absolute value bars. Nothing changed. The second one is going to be the left-hand side where the bars are is not going to change. It's going to take the bars off of it. But the right-hand side, I've got to put a negative in front of. Now this is a little bit more complicated than the other one because the other one just had one single number there, and all I had to do was put a negative in front of that number. But this one has two terms, and I have to put a negative in front of the whole side. The whole side goes negative. All right, so now that I've got my two equations, I'm going to solve them. Now this one again, I've got one that is a quadratic, so I'm simply going to get 0 on one side. I'm going to get these two terms on the other side by subtracting x and adding 5. Going to factor. Going to get the binomial x minus 5 times x minus 1, which gives me values of x equal to positive 5 and positive 1. Now, doing this side, I have to multiply through to get rid of the negative. So I'm going to have x minus 5 equals negative x squared plus 5x. And again, I have a quadratic. But this time my quadratic has a negative in front of the squared term. So in order to make it easy to factor, I'm going to actually have the squared term and the 5x move to the other side so that when I move the negative x squared, it will become positive. So I'm going to move them to the right to join x minus 5. So I'm going to have positive x squared. When I subtract 5x from both sides, I'm going to get a negative 4x here. Negative 5x plus that x over there will give me a negative 4x. And then I'm just going to have the minus 5. And again, I'm just going to factor this and get some solutions. This factors as x minus 5 times x plus 1. And I have values here of x equals 5 and x equals negative 1. Now, notice that I have a duplicate value here. So that's just really 5. It appears twice, but it's just one solution. So my solutions to this particular problem are 3 solutions. I have this negative 1, I have the positive 1, and I have the 5. So those are my supposed solutions. But remember, we need to check to see if any of those are false solutions or erroneous. And so what I'm going to do is ask you to do that check. One of those is a false solution. So what I want you to do is I want you to check all 3 of these and find out which one of these 3 is not a correct solution. Well, if you've checked all 3 solutions, you will find that for this original solution, x equals 1 does not check. When I plug in x equals 1, I get 1 minus 5, absolute value, and then I get 1 squared minus 5 times 1. That gives me the absolute value of negative 4 on the left-hand side and 1 minus 5 on the right-hand side. The absolute value of negative 4 is positive 4. 1 minus 5 is negative 4. So that is not true, and so that is a false solution. This one does not check. So what you want to do when you're doing a problem, when one of your solutions is found to be a false solution or an erroneous solution, is go back to the original problem, look at your answers, and then simply cross out the one that was incorrect. And on a test, I'll know that you checked them and you found out this one was incorrect, and that's why you crossed it out.